Let's start Unit 2, or Thermal Physics. Now, this is a much shorter unit, so hopefully we don't take more than an hour. Let's get started right away. Now, friendly reminder again, this checklist, this big list, is the list of bits or like the pieces of information you need to know in this particular chapter from the syllabus. Use it as a checklist for revision, meaning if you take a look at each one of these and you don't understand what's going on, you revise that point and you check it. Oh, I understand what he means by distinguish between solids, liquids, and gases. Oh, I know what the terms between solids, liquids, and gases mean. And you start using it as a checklist for revision. If there's a line that you do not understand, go back and revise that specific topic or ask me about it. Okay? But let's get started right away. Let's start with the kinetic theory of matter. Now, before I start like going into detail about the different states of matter, okay? One thing you have to realize, in unit 2, we are going to be describing matter two ways, the way I see it, from the outside and from the inside. What do I mean from the outside? I mean its general shape, volume, mass, temperature, pressure, the external properties of matter, like the regular properties that you measure in things. When we want to describe what happens on the inside, I mean, what happens to the molecules inside? Are they moving faster, farther apart? Are they colliding? Do they have strong bonds? Like, usually we'll describe things twice. The exam will often use the term describe or explain in terms of molecules or in terms of particles when you have to use that phrase. So be careful. Okay, I'm sure you all know this by now. Three states of matter, solids, liquids, gases. On the outside, solids have a fixed shape and a fixed volume. Liquids have a fixed volume, but not a fixed shape. They take the shape of the container they're in. Gases have no shape or volume. This means that they fill up the container. So I remember a question which asked, hey, what's the, like we used the length and width and height of a room to find the volume of the air in the room. So I needed to use the volume of the air, but I didn't have anything besides length, width, and height of the room. Well, volume of the air is the volume of the room. Doesn't matter. Then on the inside, we say that molecules have very small spaces between them in a solid, and they have regular arrangement. They're organized. The way they move is they vibrate about a fixed position, so that's also important. And they have very strong bonds or intermolecular forces between them. Okay. Next, I'm holding back a joke so badly. I'm sure you all know it. Now, molecules in a liquid have small spaces. Like, look at the difference. Very small and small. Very small and small. Don't just say, oh, liquid molecules have large spaces. They don't. They're still small spaces. And they are randomly arranged. There's no pattern. They slide over each other and they have strong bonds between them. So you have very strong in solid molecules, strong bonds in liquids. Don't use weak. I know sometimes in chemistry they use weak bonds for liquids. Not true. Not in our case. In gases, the molecules are all far apart with very large spacing and there is no arrangement. And they move free, fast, and random and with very weak bonds. You can say weak or very weak, it doesn't matter. Let's get into the important bits. What is temperature? Temperature is defined as the average kinetic energy of the molecules in a substance. Meaning, if you heat something, the molecules inside move faster, and if you cool it down, the molecules move slower. Okay. Let's start talking about temperature scales. Now, one scale is the Celsius scale in degrees Celsius. The other temperature scale is the Kelvin scale, also known as the absolute temperature scale. The difference is that the Celsius scale has negative values, whereas the Kelvin scale does not. The zero in the Kelvin scale is the lowest possible temperature. Everything else is positive. Okay? How do I convert between the two? Using the concept of absolute zero. What is absolute zero? Like the zero of the Kelvin scale. It is the lowest possible temperature at which the particles have the least kinetic energy. And that's at negative 273 degrees Celsius. Meaning, if I have the Celsius scale and the Kelvin scale next to each other, the lowest possible temperature is negative 273 Celsius. That's my zero in the Kelvin scale. Technically, yes, they stop moving. Like technically, that's the temperature at which molecules just stop moving. Okay. Which means 0 degrees Celsius is 273 Kelvin. So to convert from Celsius to Kelvin, you add 273. To convert from Kelvin back to Celsius, you subtract 273. Remember that. Moving on. I'm sure you know the differences in state. So how do I change, or when you change a solid to a liquid by heating it, that process is called melting. To change a liquid to gas, that process is called boiling. I know it's also called evaporation, but there's a difference between evaporation and boiling, and we're going to talk about that in a bit. If you cool down a gas, it condenses, and if you cool down a liquid, it either freezes or solidifies. It's the same term. Solidification and freezing are the same. The thing is, melting and freezing, as well as boiling and condensing, happen at the same temperature. We call this the melting point or the boiling point. The melting point is the temperature at which a solid can change into a liquid, or the reverse. The difference is, are you heating it or are you cooling it down? So are you the one providing it with heat, or are you taking heat away? That's the difference. So for example, and this is the only substance you memorize, ice melts to water at 0 degrees Celsius. But water also freezes to ice at 0 degrees Celsius. What's the difference? Are you giving it heat or are you taking it away? Water boils into steam at 100 degrees Celsius. Steam condenses back to water at 100 degrees Celsius. Again, are you heating or are you cooling? Okay. Very good. Now, one more thing. If I plot a temperature time graph or the heating curve for a piece of ice that maybe starts off at like negative 10 degrees Celsius or something. When you heat that piece of ice, like when you start heating that piece of ice, the temperature starts to whoop increase, but then when it hits the melting point, which is 0, it stays constant. Like it's still being heated, but it stays constant. Then when it's completely melted and now you have liquid, it's just pure water now, and you heat it, whoop, it heats up over time. Temperature keeps increasing. But when the moment it reaches the boiling point, which is 100 degrees Celsius, it stays constant again while it's in the process of boiling and changing into gas. If you can trap that gas, if you trap the steam in a container and you heat it, bad idea. But if you heat a gas trapped in a container, temperature will rise normally. How do we explain this in terms of energy and particles? When the temperature is increasing, again, when the temperature is increasing here or here or here, it's increasing because the kinetic energy of the molecules is increasing. Molecules are moving faster. But during melting and boiling, like during both of these processes, the temperature remains constant, which means the kinetic energy is not increasing. How is that possible? I'm still giving it heat energy, so there is no increase in kinetic energy. The energy absorbed is used to weaken or break the bonds between the molecules. So during the melting process and the boiling process, the energy absorbed is not used to increase the kinetic energy, is used to break the bonds between the molecules and move them farther apart. This is why the temperature stays constant during melting and boiling. Okay? Yeah. Remember, there's a difference between boiling and evaporation now, even though they're both the change in state from liquid to gas. So what is evaporation? Here. Evaporation is when the most energetic molecules, like you have to memorize some of these definitions. This unit is a very wordy unit. You have to describe a lot. It's when the most energetic molecules on the surface of the liquid break their bonds and escape. So evaporation isn't, oh yeah, liquid can boil anywhere. No. It happens normally at any temperature. You don't need it to be at the boiling point, but it only happens to the molecules on the surface and only if these are the most energetic molecules of them. Because not all the molecules have the same energy. Some have a lot, some have a little bit. And that's proven by the definition of temperature, if you remember. We said temperature is the average kinetic energy of the molecules in a substance, which means inside any substance, the molecules are not all moving at the same speed. Some of them are very fast, some of them are slow, and then they obviously collide or like they slide around and they change speeds. But when a very high energy molecule is on the surface of the liquid, it uses that energy to escape. It breaks the bonds and escapes. But if the most energetic molecules escape, less energetic molecules are left behind. So the temperature of the remaining molecules, so the rest of the liquid, starts to cool down. This is why if you go swimming and you get out of a swimming pool and you just stand there in the air and the wind, you start feeling cold. Not because the weather is cold, like nowadays, sure, but even in the middle of summer, you start feeling chilly. Why? Because the liquid on your body starts to evaporate. So the remaining liquid that's still on your body cools down and it absorbs heat from you. You cool down. Okay? There are three ways to speed up evaporation. You can increase the rate of evaporation by either increasing the temperature or increasing the surface area, because this means you have more molecules on the surface, or allowing air to move over the surface. We call these air currents. Turn on a fan, blow on your soup. All of these things would cool down your liquid because it increases the rate of evaporation. Okay. If I ask you what's the difference between boiling and evaporation? They're both from liquid to gas. One, evaporation happens at any temperature, whereas boiling only starts at the boiling point, so 100 degrees for water. This one is basic, but you see bubbles during boiling, but you don't see bubbles during evaporation. And this one's important because this was part of the definition of evaporation. Evaporation only happens to the most energetic molecules on the surface, so there's a condition. Boiling doesn't have that condition. Sure, it has a condition, which is at the boiling point, but then it doesn't have a location condition. Everything boils. All the molecules throughout the liquid boils. Evaporation only occurs here. Then during boiling, the temperature stays constant. That's what we said earlier. However, during evaporation, the temperature decreases. Those are the differences. Okay, very good. Let's solve a few questions to revise these specific topics. So let's start with our first question. State the value of absolute zero. Now, it's 0 Kelvin, but in Celsius, it's negative 273 degrees Celsius. Explain what is meant by the term absolute zero. Refer to particles in your answer. So absolute zero is the temperature at which the molecules or particles, if you said particles, I'll use particles. The particles have the least amount of kinetic energy. So absolute zero is a temperature where the molecules in a substance have the least amount or almost no kinetic energy. Okay? Next question. 4 students describe the phrase absolute zero during a session. Which statement is correct? This is the lowest possible temperature. I mean, he's right. But let's read the rest. Particles in a solid start vibrating. No, they're always vibrating. That's not the temperature at which they start vibrating. Right? On the contrary, technically, based on what you asked earlier, this should be the temperature at which they stop moving. So, yeah. Particles do not have weight. Absolutely no significance to our discussion. Particles have the least gravitational potential energy. Come on. Least kinetic energy would be fine. Okay, good. Okay. Nice. So going back, I always want you to add one more thing. Don't just say it's the temperature at which the particles have the least kinetic energy. There's always a second mark. The lowest possible temperature at which particles have the least kinetic energy. Because if you think about it, would least kinetic energy give you 2 marks? Lowest possible temperature. Particles have the least kinetic energy. Done? Good. You've memorized it. Next. Which statements about evaporation are correct? Evaporation causes the remaining liquid to cool. Yes, it does. During evaporation, the more energetic particles escape from the surface of the... Absolutely. Evaporation only happens at 100. Nope, that's for boiling. So 1 and 2. So B is my answer. Moving on. During a picnic on a warm day, dry day, a metal can of lemonade is wrapped in a damp cloth. Whenever I say the word damp, I want you to immediately think of evaporation. Because damp means this cloth is wet. And if the day is warm and dry, but the cloth is wet, what's going to happen in the cloth? It's going to cool down because it's going to evaporate. The liquid inside it will evaporate, right? So the remaining molecules will be cooler. So they will absorb heat from the can, which will cool the lemonade. It's a very, old method of cooling something down. Explain the evaporation cools the water in the cloth. Come on, he's spoiling the fun. Explain in terms of molecules how evaporation cools the water in the cloth. So let's discuss this in detail. The most energetic molecule on the surface of the liquid break their bonds and escape. So the remaining molecules have less average kinetic energy, cooling the water in the... Now, I would not have probably mentioned everything, like most energetic molecules on the surface of the liquid, if it wasn't worth 3 marks. Because if it was just about how does evaporation cool the water, I would just say, oh yeah, when the most energetic molecules escape, the remaining molecules have less average kinetic energy. That's worth 2 marks. I have to describe a little bit more. I have to start the evaporation process from the beginning because it's worth 3. Next. As the water in the cloth cools, so does the lemonade. Explain how electrons transfer thermal energy through the metal of the can. This is more of a question about conduction. It's not really an evaporation question. It's a conduction question, which means we'll go over this at the very end of the lesson. So if you still don't remember what conduction is, that's fine. Watch till the end and skip back and come back to this answer. But how do electrons transfer thermal energy through the metal of the can? Imagine this is your can of lemonade. You've wrapped a cloth around it. Actually, we should color the cloth blue. We've wrapped a wet cloth around it. So if I cut a cross section here so that you can only see what happens inside the wall of the can. Here's your can. Here's the cross section of the can. Here's the cloth. That's wet. And here's the, oops, sorry, my bad. Here's the cloth, here's the can. And here's the liquid inside. He has lemonade inside. I'm not going to go for it yet. Just lemonade inside. So conduction is the name of the process, right? Conduction is the name of the process. But the way this works is this. When the liquid molecules escape from the cloth is now cooled, which does what? Which absorbs heat by conduction from the surface of the can. This causes electrons on the lemonade side to take that heat, to take heat from the lemonade, they absorb heat from the lemonade, and they move through the body of the can to where the cloth is. And that transfers heat, what? Outside of the can. This is how the can cools down. This is how the can cools down. So explain how electrons transfer thermal energy through the metal of the can. You could start with the electrons, or you could start with the lemonade, or you could start with the cloth. I'll start with the lemonade, so I don't have to explain, like go back and forth in my mental explanation here. So heat from the lemonade is absorbed by the electrons in the, one more, XSE, electrons in the metal can. Right? The electrons then travel to the other side of the can. Here's the question, why? Why would the electrons move? Because they move from hot to cold. They move from high temperature to low temperature, right? We can say the outside of the can, that's better. Moving from hot to cold. You can do that, or moving from or through the temperature gradient, or from high temperature to low temperature. Transferring that heat to the fuel. Okay, very good. So this was very descriptive. You'll notice there were barely any calculations here. So let's move on to the next bit of this unit, which does include a little bit of calculation. Let's talk about thermal expansion, which is the increase in volume of a substance when the temperature increases. But also, let's talk about the gas laws, because they all are related to an extent. First, what is thermal expansion? Thermal expansion is the increase in volume of a substance when its temperature increases. If I ask you to explain why it happens, like when you heat something, the volume increases. Why does that happen? Because when it happens, the molecules move faster and farther apart. So if you take a look at this little sketch over here, look at this, look at this. This sketch is so cute. Now, the molecules, when they heat up, they also move farther apart. So if the space between the molecules increases, the entire volume of the substance increases. Never, ever say the molecules or particles expand. This is a crime. You'll be arrested as you solve the paper. Like imagine that. Okay, molecules expand. Cambridge just walks in. Okay, you don't deserve to know physics. They kick you out. Molecules don't get bigger. This doesn't happen. So when you say molecules expand, you mean the molecules themselves get bigger. They don't. They move farther apart. Is that clear? F in chat if you write A. Molecules expand. Anyway, how do we increase the amount of expansion? Now, this kind of makes sense. Temperature, obviously, if you heat something up, it expands more, so that makes sense. The greater the initial volume of the object, the more it expands, which also makes sense because if you have an object that's initially very small, like let's say 2 molecules wide, when you heat it, it barely moves away from each other, like they barely move away from each other. So the volume barely increases. But if you have an object that's originally 4 molecules long and you heat it, each one of these molecules needs to move further from the other. So the overall expansion is much larger. So the initial size of the object matters. Bigger objects expand more. More liquid expands more. But most importantly is the state. Gases expand more than liquids. Liquids expand more than solids because gases have very weak bonds in the molecules, whereas liquids and therefore solids have stronger A bonds. Okay? So it's easier for gases to expand than liquids and easier for liquids to expand than solids. If I ask you to suggest, and it doesn't show up very often, but if I ask you to suggest a use, not a consequence, not a harm, not a bad thing, a good thing, a good use of thermal expansion, there are three things that should probably come to mind. The last one, probably not. But first is a thermometer, like a basic liquid in glass thermometer, like this one. When you heat it, the liquid inside expands and bloop, goes up. So that's a use of expansion. We use thermometers to measure temperature. Then we can use thermal expansion to fit rings, metal rings on top of wheels. If I have a wheel from a train, for example, and I want to fit a ring on top of it without using glue or nails or screws or anything, or even welding it, we get a ring, a metal ring, that doesn't fit, like it won't fit on top of that wheel. Heat it so it expands a little bit, fit it on top of the wheel, and let it cool. It'll grab onto the wheel and it gets stuck there. So when you heat the ring, it expands, you can fit it on top of the wheel. Then finally, what we call a bimetallic strip. Again, a bimetallic strip. The word bi means two, metallic means made of metal. So we have two different types of metal stuck together. This is a very weird application though. Like it's used a lot, but you never see it yourself. If you have two different metals, like this blue metal and black metal over here, if you heat them, each metal will expand by a different amount. Let's say the blue one wants to expand more than the black. That can't happen. Why? Because they're stuck together. So they're forced to stay stuck together. They can't separate. So what they do is they bend. Remember, if you have a slice of pizza, I know some of you are hungry already. If you have a slice of pizza, the outer length of the arc, like the further away, the larger the radius, the arc's length on the outside is greater than the arc's length on the inside of the crust. Like imagine you have a nice thick stuffed crust full of cheese, pepperoni slice of pizza. So this one is longer, this side is shorter. So that's what a bimetallic strip does. When you heat it, it bends, it curves. The metal on the outside of that curve is always hotter. Here's the thing, though. What do I use it for? It's often used inside devices like thermostats or fire alarms, or in more modern times, uh, air fryers. How do you think when you set the dial for an air fryer, when you turn it to the right to increase the temperature, how does that work? Inside is a screw and a bimetallic strip. Remember, the bimetallic strip will bend and therefore open a circuit, right? Open a circuit if it gets too hot. So by turning the screw, we push that in and we make sure to 100% touch the bimetallic strip, even bend it a bit. So when it heats up, it doesn't need to bend yet. So when it hits, let's say 150 degrees, it bends enough to leave that, screw. What if I wanted to reach a higher temperature? I screw it in some more. So that's just a basic concept. You don't have to understand it fully, but know that it's inside all of these devices. Okay. We have a question. Don't we use alpha particles in fire alarms? Yes, we do. This is why we say these are for old fire alarms. They weren't very good, by the way. You would wait until the fire alarm itself got hot from all the smoke and stuff. And then when the bimetallic strip would curve to touch part of a circuit and ring the bell. That was really bad and very slow. Next. What about the problems caused by thermal expansion? Three general problems you should probably remember as well. Problem number one. Let's zoom out again. Problem number one. Railway tracks. They deform, you can say deform, buckle, or bend when the temperature increases. How do we solve this? Like they deform like this when the temperature increases. How do we solve this? We leave gaps between sections of the track. This allows the railway track to expand during the summer without bending and contract again during the winter. Okay. Next, The same problem can happen not just with railway tracks, but with bridges and roads. So whenever we build bridges, we usually build them in sections and we leave very thin gaps between them. They don't need a lot, but we do leave thin gaps because if they expand and we don't let them, like they're fixed with no gaps, the concrete will crack. Bad idea. And then electric cables that are hanging. Now, hanging cables have two problems. During the summer, if they get too hot, they could expand so much that they touch the cars down here. Who knows what happens to you if the very super high voltage 200,000 volt cable touches your car as you're driving through. Okay? But if it gets too cold, like during the winter, the issue is the opposite. I'm not afraid of expansion. I'm afraid of the opposite. I'm afraid of contraction. So the cable contracts, gets shorter, but if it gets too short, click, it tears apart. Or maybe it rips apart where the pylons are. So the cables cannot be too long. Besides costing us money, it'll expand and touch the people on the ground. And if it's too short, the problem during the winter is that they'll contract and rip apart. Both of them are bad ideas. Okay. That was thermal expansion. Let's talk about gases. Now, when it comes to gases, I want you to think of three things, not one thing, three things. One is the concept of Brownian motion. Two is how does a gas apply pressure? Not what affects the pressure. How does a gas apply pressure? And then three, what affects the pressure? So we'll see two things that affect pressure here. But first, what is Brownian motion? What is Brownian motion? If you get some gas, smoke specifically, inside what we call a smoke cell. So you trap some smoke from, some burning wood, some incense, a cigarette, it doesn't matter. Obviously, don't smoke, kids. It's bad for you. I don't smoke. Smells really bad too. Like, I don't understand smoking. And you look under a microscope, you won't see the smoke. You will see small dots of light. We call them specks of light because they reflect the light from the microscope's light source. And these specks of light will be moving around randomly and irregularly, or random and jerky, or random and zigzagged. The idea is, number one, it keeps changing direction randomly. And number two, when it changes direction, it's not smooth. That's what the term irregular or jerky means. It suddenly changes direction as if something hits it. And that's what happens. Smoke particles, if you didn't know, are solid. They're not gas. Smoke particles are dust particles that are solid. And these dust particles that are floating around in the air move around because of the random collisions of the air molecules with the smoke, meaning each smoke particle is surrounded by thousands of small air molecules we don't see. And these air molecules collide with the smoke as they're moving randomly from all directions. So it's literally being, a smoke particle literally is being slapped around. Poof, poof, up, down. Okay, you go left, you go right, you go up. And the more you heat the gas or the air, the more it gets slapped around. So it moves more random and jerky. And if you cool down the air, it moves less random and less jerky. It doesn't change direction much. It's not the fact that the smoke moves slowly. It's the fact that it doesn't change direction much when the gas is cooled because the air isn't moving as fast. Okay? This experiment can also be done not with smoke particles, but with pollen grains in water. The exact same results will apply. If you get a Petri dish of water and you put small bits of pollen in there, so pollen in here, and you look under a microscope, you get the exact same phenomenon. Okay? Good. Next. Let's talk about gas pressure. First, how does a gas apply pressure? Not how does the pressure change? How does the gas apply pressure? This is one of those things that you have to memorize. It's vital in exams. Okay, this is very important. What is this? Let's read the description first. So how does a gas apply pressure? Gas particles, as they're moving freely or fast, they collide with the walls of a container. So imagine you have a little gas particle trapped inside a box. As it's moving, boom, 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 keeps colliding. And when it collides, it experiences a change in momentum. Remember momentum? When you collide, you change direction. So that's a change in momentum. That change in momentum over time applies force, because that was Newton's second law. Force is equal to change in momentum over time. So every time a gas particle collides with a wall, it experiences a change in momentum. And that change in momentum over time is what applies force. Now, I asked about pressure, not force. So remember, this applies force over the area of the walls. Force over area is pressure. Applying pressure. So you have to mention the following. Gas molecules collide, it's very important, experiencing a change in momentum. Change in momentum per time applies force. Force over area applies pressure. This is often worth 3 to 4 marks. You have to mention all of these things. Okay? Yeah. There are two things that affect the pressure of a gas. Temperature makes sense, and volume also makes sense. If you heat a gas, temperature increases, the pressure increases. So temperature and pressure are directly proportional. This makes sense because if you heat a gas, let's look at this diagram over here. If you heat a gas, the molecules inside start moving freely, poop, 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 colliding, and they move faster, and they collide harder, and they collide more frequently. So the pressure increases. So you have to mention a few keywords here. Keywords. The gas molecules move faster, so they collide harder, or you can say with more force, and more frequently, meaning the number of collisions increase. Stronger collisions and more frequent with the walls of a container. Okay? So temperature and pressure are directly proportional. If the volume is constant, like if I keep the gas trapped, because if you don't keep the gas trapped, it'll expand, so the pressure doesn't change. However, what if I don't change the pressure? What if I compress the gas? You can do that by either putting a gas in a cylinder or in a balloon. If you sit on a balloon, that's an act of decreasing or changing the volume of the gas with no change in pressure. So volume and pressure are inversely proportional, meaning if you take a look at this cylinder again, and you start compressing the gas, you push this piston in, you decrease the volume, you trap the molecules in a smaller space. The molecules will not move faster. They're not moving faster because speed depends on temperature. They're just colliding more frequently because the space between them decreases. Okay? Space between them decreases. So keywords to answer, if I ask you to explain why this happens, the space between the molecules decreases. They're not moving fast. So they only collide more frequently. They don't collide stronger, because that depends on speed. They just collide more frequently because you trap them in a smaller space. Finally, this last relationship has an equation or a rule behind it, which is PV equals constant, or my favorite, P1V1 equals P2V2, meaning the pressure times volume before a compression is equal to the pressure times volume after you compress it. Okay? Yeah. Sometimes if I can ask you, and this is often shown in multiple choice questions, to choose a graph which represents the relationship between pressure and volume. Since pressure and volume are inversely proportional, this negative curve is what you sketch. By the way, this negative curve is what you sketch if anything is inversely proportional to anything else. So the graph for inverse proportionality is always this negative curve. Okay. Let's solve a few questions. First, the temperature of a fixed mass of gas is at constant volume is decreased. So he's mentioned a change now. Temperature is decreased and the volume is constant. Keep that in mind. Constant volume, but the temperature decreases. So the pressure is going to what? Decrease because the molecules are now moving slower. So they collide with less force and less frequently. So state and explain in terms of particles. Look at this. Look at this. Look at how he's phrasing the question, huh? If you just said state how the pressure changes, pressure decreases. State and explain in terms of particles how the pressure changes. Keep that in mind. So let's go. The pressure decreases. Why? Because he used particles, so I'm using particles. Also, let's say molecules, but I tried to say particles, so got messed up. The particles do what? Move slower, so they collide with less force and less frequently with the walls of the container. Do you mention momentum or change in momentum or force over area? No, you don't. When we describe changes in pressure, you don't mention the whole momentum story. You only use that when I ask you to explain why there is pressure. Okay? Next. Cylinder 1 contains 350 centimeter cube, that's volume, of a gas at a pressure of 9 times 10 to the power of 4 Pascal. The moment you see volume and pressure, immediately think of P1 V1 equals P2 V2. The gas is then transferred to cylinder 2, and the pressure increases to 1.6 10 to the power of 5 Pascal. So that's P2. This is P1, this is V1, this is P2. He's probably going to ask for V2, right? What's the volume of cylinder 2? P1 V1 equals P2 V2. P1 is 9 times 10 to the power of 4. V1 is 350 equals P2, which is 1.6 10 to the power of 5 times V2, and V2 is your subject. So 9 10 to the power of 4 times 350 over 1.6 10 to the power of 5. And you work it out. By the way, when we start solving past papers in the future, there are a few tricks that you need to keep in mind with this specific chapter. Here, there isn't a very hard trick. It's a 3-mark question, but it's not a very hard trick. The unit's going to be what? Centimeter cubed. The unit's going to be centimeter cubed. Sometimes this question could be worth 4 marks. It gets a little bit harder. Or sometimes it's 3, but it's just a bit harder. We'll see that later. Okay. Next, state which state of matter, solid, liquid, or gas, has the greatest thermal expansion and which is the least. So which one expands the most? Gas. Which one expands the least? Solids. Then describe in terms of motion and arrangement of particles, the structures of solids and gases. So now you're just comparing solids and gases, but keep in mind, sometimes the question will ask you to specify specific properties, like motion, or bonds, or arrangement, or like, so keep that in mind. Here it's just motion and arrangement. So the solid particles vibrate about fixed position and are regularly arranged. Gas particles move freely, fast, and randomly with no arrangement. You want to add bad, they're close together, far apart. That's not going to hurt, but these things have to be in your answer, like the motion and the arrangement. Because the question literally asks for that. Okay. Next. A student uses a microscope to observe pollen grains moving or pollen moving on the surface of water. Which statement describes the reason for this movement. So water molecules are moved by the pollen. Look at the order. No, it's not the water that's moved by the pollen. It's the pollen that's moved by the water. So it's the water that collides with the pollen, just like how the air molecules collide with the smoke. So water molecules are moved by pollen, no and no. And then microscopic pollen particles are moved by water molecules. And then pollen molecules are moved by water molecules. Which one do you think you should use? Look at these two. This is one of the very few times like paper 2 becomes irritating. Which one do you think is correct? I want you to guess. Guess in chat. Yalla. Guess in chat. Okay. Okay. So I see a bunch of different answers. That's nice. Oh, I see a lot of people are choosing the same answer now. That's also nice. That's fine. Okay. So a lot of only a few people chose D, which is good. The correct answer is what? C. Why? That's a very important thing to ask. Why is it C? Look at the language. Look at the language. Microscopic. Because what do we use to see pollen grains? A microscope. They're small. This is what you need to understand. Even these are very small. Okay? Microscopic pollen particles are moved by water molecules. No, it's not because the small particles hit the big. Keep in mind, the water molecules are even smaller than the pollen particles. The water molecules are even smaller than the pollen particles, right? But the first key part is particle versus molecule. Usually particles are used for things that are bigger than molecules. Molecules are smaller. Usually. That distinction isn't always fixed, however. But because we need to identify that even the pollen particles are small, which is why we need a microscope to see them. But if I have just pollen molecules, wait, are they the same size as the water? Like you're trying to say, oh, they're the same thing. Pollen and water are the same. No, they're not. Pollen particles are still larger. So we use the word particle here instead of molecule. And microscopic just means they're small relative to us. Okay? Okay. Next. The second and only other calculation left in this unit, specific heat capacity. When you heat a substance, it takes energy from you. You need energy to heat it. How much you heat it depends on a few things. How much do you need to heat it depends on a few things. But first, let's define energy in the first place. Internal energy, another way of saying heat energy, is defined as the total kinetic energy of the molecules, not the average, the total, like all of the energy. Okay? Right? Then, specific heat capacity, however, is defined as the energy needed to raise the temperature of 1 kilogram by 1 degree Celsius or 1 degree Kelvin. This means that each material needs a certain amount of energy to get hot. Like, take this for example. If I have a block of metal, let's say I buy a dumbbell, like a 1 kilogram dumbbell. It's kind of small, very small, made of iron. If it's currently at 20 degrees Celsius and you start heating it up, like put it on the stove to heat it up, in order to heat this iron dumbbell, a 1 kilogram iron dumbbell, from 20 to 21 degrees Celsius, you need about 450 joules. You don't memorize values though. You need about 450 joules. This is what we call the specific heat capacity of iron. It's the amount of energy you need to raise the temperature of 1 kilogram by 1 degree. Which means if I want to heat that iron by 100 degrees, I need 100 times that energy. So you multiply the change in temperature by 450, the specific heat. Or if you have a 10 kilogram dumbbell, now that's better. That will give you a little bit better of a workout. and you want to heat it by 1 degree, you need 10 times the amount of energy. Which is why the formula that we use to calculate energy is E equals mc delta T. Again, E equals mc delta T. E means energy. M is mass. C is specific heat, capacity, obviously. And delta T means change in temperature. Let's try making this thinner. It's too thick. Yeah, this is much better. Change in temperature. So T2 minus T1, final minus initial. Okay, which means if you want to get C, which is the specific heat capacity, what do? Make it the subject. C is equal to E over m delta T. The unit of measurement of specific heat capacity is joules per kilogram or gram, sometimes it's gram, degree Celsius or degree Kelvin. So joules per kilogram Celsius or joules per gram Celsius. Yeah. A very common experiment that we use to find the specific heat capacity of any substance is using these rules, by the way. If I want to find the specific heat capacity of a substance, it's E over m delta T, which means I need to measure the mass. So that's easy. I use a balance. Right? To measure mass, I use a balance. Then I need to measure the temperature. So I use a thermometer. So I measure the initial thermometer. Initial temperature using the thermometer. Then you put a heater inside, usually an electric heater. Here's the thing. You have no way of measuring energy. But from unit 1, if you remember, energy was also power times time. Energy was also power times time. Because power is energy over time. So in order to find energy, I need the power and the time. Sometimes the power is given to you. It's like, hey, this is a 30-watt heater. That's nothing, by the way. This is a 1,000-watt heater. That's a lot better. So you have the power, and I use a stopwatch to get the time. Or sometimes, as we saw last time, I can mix this up with electricity. Power in electricity is V times I. The important thing is we get power, either given to us on the device or we measure it using VI. And then you measure the final temperature after you heat something up. Like let's say you heated up that iron or you heat up the liquid by a certain amount. And you measure the time using a stopwatch. And substitute. Energy is PT, mass is M, T2 minus T1, and you get C. Okay? Now, one extra bit. I'd like you to write that in your own notes, okay? One extra bit. Does the value of C, or is the value of C always going to be accurate? Obviously not. There's no such thing as 100% accuracy in anything. But specifically in this experiment, there are sources of error. And it's a very common one in thermophysics, which is what? Heat loss. You're busy heating the iron. Who said the iron isn't heating the surroundings? So when you're doing this experiment, you're actually losing heat to the surroundings. That's bad. Because that means the final temperature that you're using, delta T, the final temperature is lower than what you want, which means the change in temperature is lower than what you want. You're trying to heat it to 100, it actually heats up to 90. So the specific heat capacity value you get will be higher than normal. The solution to all of your problems in thermophysics is almost always to insulate. Cover this thing with an insulator. That'll stop it from losing heat to the surroundings. Or if it's a liquid, that's even easier. Cover the beaker or the container with what? With a lid. With a lid. Why? Because that stops or reduces the heat from escaping through convection and evaporation. So it stops the hot air from rising, stops the liquid from evaporating, or at least the heat loss. So you get the proper temperature, the correct, accurate measurement of temperature. Obviously, if you insulate it, that's even better too. Why is the final temperature should be higher? Like imagine this, imagine this. You give the substance 1,000 joules of energy. This 1,000 joules of energy should have heated it from 10 degrees to let's say 50 degrees. But because you haven't insulated your setup, you lose some energy. Not all the 1,000 goes to the metal or it goes to the water. You lose a little bit. So instead of it reaching 50, it reaches 40 degrees. Is this accurate? Like you gave it 1,000. It should have reached 50 with that 1,000. Nope, it only reached what? 40. So if you look at the mathematics here, m delta t, if you substitute this with power times time, like, oh, I gave it 1,000 joules, power times time. The delta t should have been 50 minus 10. No, it's actually 40 minus 10. This value is smaller than what you expected. So the value of the specific heat will be higher than what you expect. It'll be inaccurate because they're inversely proportional in the formula. Okay, good. Very good. Let's solve a question then. Define specific heat capacity. Let's copy it. The amount of heat energy or thermal energy needed to raise the temperature of 1 kilogram by 1 degree. I don't have the degree. You can use the degree. By 1 degree Celsius. Okay. Or of a unit kilogram or of a unit mass by unit degree temperature. A student carries out an experiment to determine the specific heat capacity of a metal. A cylinder of the metal is heated by a 12-watt heater. So it's heated by, here's the power. State the readings the student should take. So what should I measure? Besides power, like that's given. Look, it's already given. So this is solved for me, yay. Look at the equation. C equals E over M delta T. Oh, I don't have E. I need power times time over M delta T. So the things that I need to measure are the mass. It's just state. I'm not explaining. The mass of the metal, the initial temperature, and the final temperature of the metal. So T1 and T2, and the time taken to heat the metal. Like this answer could have been much shorter if I said mass, initial and final temps, time taken, done. Next. Use another one, but this one's a good one. This will use something we mentioned before, earlier on. Figure 5.1 shows an electric heater used to heat a room. The dimensions of the room are 4.5 by 6.1 by 2.4, length and width and height. The density of the air in the room is 1.2 kilograms per meter cubed. Remember, show questions are just like calculate questions, but you need to be very clear with your working. You can't just expect the examiner to figure out what your scribbles mean, okay? They're not cryptologists. Is that the term? I must have forgotten. Anyway, show that the mass of the air in the room is 79 kilograms. Density is my key point here. So density is mass over volume, which means mass is density times volume. Oh, I have the density. That's fine. 1.2 times. What's the volume that I should use? The volume of the air is the volume of the room. Bravo. We mentioned that earlier, huh? And I have the length and width and height of the room. So it's 4.5 times 6.1 times 2.4, which is equal to, calculate the time. 1.2 times, 4.5 times, 6.1 times, 2.4. 79.056, so 79.1 kilograms. Done. Show the rule, show the proper substitutions. Don't just like skip this, like don't type this in your calculator and just say, oh, sorry, I did it on my calculator. It's a show question. You have to show how you got the volume. Okay, next. Remember, now we have the mass. It's a value. Even if you couldn't get this, it's a value that you have. The power of the heater is 1,100 watts. So you have the power. Specific heat capacity is 1,000 joules per kilogram. Calculate the time taken to increase the temperature from 16 to 20. So E equals mc delta T. That's the primary rule we have. But I don't have energy. He wants time and we have power. Oh, so the moment you see this, I want you to replace E with power times time. The moment you see the question using power and asking for time or giving you time and power or something like that, just replace E with PT, which means T is equal to mc delta T over P. The M is 79. I'm going to assume you couldn't get this. So 79, I'll copy the value he just given me, times C, which is 1,000, times delta T is the change in temperature. So 20 minus 16, which is 4 degrees, over power, which is 1,100. Over 1100. 287.272727. Okay, that's enough. 287. Now, because we're using SI units, seconds is my answer. Because we're using SI units, seconds is my answer. Okay? Very good. This isn't hard at all. Next. Suggest one reason why the time calculated in AII is the minimum time needed to increase the temperature of the air. Why? Why is it the minimum? Has to do with what we mentioned, by the way. Why is this the minimum time needed? Because here's the thing. Who said the heater is just heating the air in the room? Like, come on. You have the room, but then you could have a chair in the room. All right? You could have a TV in the room somewhere. You could have a PS5. I know I don't. They're really pricey these days. All right? You could be sleeping in the room. Maybe. But the important thing is the heater isn't just heating the air. It's heating what? Other things. Like the chair, like the TV, like this, cadaver on the ground. All right? Or maybe you're losing some heat through the window that was broken somewhat for some reason. Like, I don't know who broke the window. But it could be leaving out through the window. So there's always some heat loss. Is it a crime scene? Nah. Dude's just sleeping forever. Now, I'm sorry. It's funny how his PS5 is still there. So why? Due to heat. Now, here's the thing. Most students do this. Heat loss. Or heat loss to the surroundings. Now, most of the time this works. Here it doesn't. Want to know why? Because usually the surrounding means the air. Here we're trying to heat the air. So you have to be very specific as to what you're losing the heat to. Oh, some of the heat is lost to the furniture, for example. All right? Or lost through the walls or the window outside of the room or out of the room. So you don't always heat exactly what you think it is. Don't just use the word surroundings nilly-willy. Be specific. What do you mean by the surrounding? The surrounding air, the surrounding furniture, the surrounding walls, through the walls? Be specific. Okay. Let's finish up this discussion by this is a huge checklist, by the way. Why is it minimum, Bardo? It's minimum because here's the thing. This is what you're assuming the time the time that's needed to heat the air if there's no heat loss, right? Like you're assuming 100% of the power is going to the air, right? You can't heat it up any faster than 287 seconds. But if there's heat loss included, it'll definitely take more than 287 seconds. But it cannot take less than 287 seconds because this is assuming 100% efficiency. Okay? Nice question. Now, this is a giant checklist, but that's because this last bit is split into like 3 different sections. Heat transfer is often, or heat is often transferred through either conduction, convection, or radiation. These are the 3 methods of heat energy transfer. So let's start with conduction. Conduction is the primary method of heat transfer through solids. But depending on whether a solid is a metal or a non-metal, the way you describe conduction changes. In a regular non-metal, you have atoms, or sometimes we say a lattice, a molecular lattice. When you heat one end of that solid non-metal, the atoms vibrate and transfers heat to nearby atoms only. So it's a very slow process. But in metals, you have an extra advantage. Metals have free moving or delocalized electrons. So when you heat it, not only do the atoms vibrate and heat up nearby atoms, the electrons also get hot. And the electrons aren't limited to nearby atoms. Electrons can move freely through the metal. So the electrons can move freely to the other end of the metal, heating distant atoms. So when you're describing how conduction occurs in metals and nonmetals, in nonmetals, the atoms vibrate and transfer heat to nearby, keyword, atoms. In metals, the atoms vibrate and transfer heat to nearby. Like this also happens. So there are 2 processes, the regular vibrations and free moving electrons travel to distant atoms or transfer heat to distant atoms. Okay? So you know what good conductors are. All metals, I'm sure you're familiar with copper and iron and steel and, constant tan and nickel and chrome and aluminum. Bad conductors are also called insulators, are things like plastic and rubber and wood and glass and liquids and gases. All of these are bad conductors of heat. But since liquids and gases are bad conductors of heat, there's another method of transferring heat for them, right? For now, I'm limiting conduction to solids. It doesn't mean that liquids and gases do not conduct. There's a difference between saying do not or does not, like no conduction, and poor conductors or bad conductors. They do conduct, but very poorly. Okay? Really quickly, though, sometimes you'll be asked to explain an experiment to demonstrate if something is a good or a bad conductor. Easiest thing to do, it's usually a rod. You get the rod, you stick a few ping pong balls with some wax. The reason why we use wax or a hot glue gun, like wax is basically the glue from a hot glue gun. You just use that and you stick it to the ball, to the rod, I mean. And then if you heat this end of the rod, if it's a good conductor, the heat zooms through the rod and therefore melts the wax along the way. If it's a bad conductor, the heat doesn't go through, or it goes through very slowly. So how do I know which is the best conductor? The one that makes more balls fall, or the one that melts more wax? The bad conductor doesn't melt a lot of wax because the heat isn't even traveling through very well. Okay, very good. Okay, before I move on to convection, I have a question here. Does conduct mean it does a good conductor absorb it better, transfer it? Okay, no. Conduction means it's a good material to transfer heat through the substance. Has nothing to do with absorption of heat. Has everything to do with transferring the heat through. Absorbing that relies on your heater, if it's a high specific heat or a low specific heat. Regardless, you're heating it. But whether it transfers the heat quickly or slowly, that's another thing. I'll give you an example. If I get a metal spoon, like a long metal spoon, like let's say I'm gonna go cooking in the kitchen in a bit when we're done with this class, and I get a big metal spoon and I put it on top of a fire, like one end over a fire. It's gonna get hot, and my hand's gonna get hot because it transfers heat through to my hand. Good conductor. If I get a wooden spoon, put it on top of the flame, does the wooden spoon not absorb the heat? It does absorb. The key word isn't absorb. It does absorb the heat. But does it conduct the heat through the wood to my hand very well? Or would it rather burn where it is, absorb all the heat, stay where it is, and it doesn't conduct the heat very well? So there's a difference between conduction and absorption. Keep that in mind. Okay? You're welcome. Next up, how does heat get transferred through liquids and gases then? By convection. How does convection occur? That depends on thermal expansion. If you have a liquid and you heat it, the liquid or the gas, the liquid does what? Get hot, obviously. And it expands, and the mass doesn't change. So when you heat something, the mass doesn't change, but it could expand. So if something expands, but the mass doesn't change, the density decreases. So it becomes less dense, and it rises up. The cold liquid, on the other hand, because it's colder, like if you put a piece of ice in here and it cools down the ice, the temperature is lower, it has a smaller volume, same mass, so it's more dense and it sinks. Same thing with the air in the room. If you have an air conditioner, it cools the air, which causes the cold air to sink because it's more dense. A heater would heat up the air, making it expand. It becomes less dense, so the hot air rises. This flow, this flow of air or liquid is called convection. This flow is called convection, and the flow is called the convection current. So how do I explain it? Very briefly. Hot stuff rises, cold stuff sinks because hot is less dense than cold. Liquids or gas doesn't matter. Okay? Finally, there's a third method of transferring heat. And that method is called radiation. What is radiation? It's just a type of wave. It's a type of electromagnetic wave that transfers heat. Infrared waves, to be specific. Everything emits infrared waves. Everything. I emit infrared waves. You emit infrared waves. The room around us is currently emitting and absorbing infrared waves. My phone is emitting infrared waves. Infrared waves are invisible. They travel in all directions in straight lines, and they can travel through a vacuum, but they transfer heat, not light. Okay? Everything emits that. So the heat that comes from the sun, that's due to radiation. If I put my hand next to a fire, not above a fire, if I have a fire and I put my hand next to that fire, it doesn't matter if I'm missing a finger, it's a cartoon hand. The heat that comes to my hand, that reaches my hand from the fire cannot be by conduction because air is a bad conductor. It's not convection because hot air would convect upwards, right? So the heat that reaches my hand sideways is only through what? Radiation. It's only through radiation. Now, three things affect how much a surface emits radiation, if it's hot, or absorbs radiation, it's called. Surface area, So the larger the area, the more radiation can be emitted or absorbed. The temperature, the higher the temperature, the more radiation can be emitted. Right? So the hotter you are, the more radiation you can emit because you have more energy. And the third factor, arguably most important, is color. It's color. Two specific colors. Dull black, so think matte, not reflective, not shiny black, and shiny white, think silver, something that's polished and bright and reflective, reflects everything. We say that black is the best absorber and emitter of radiation. White is the worst absorber and emitter of radiation. Do you know what that means? This means if I have two metal cans, like you can use this experiment to distinguish between like good and bad emitters. But if I have two metal cans, right? Here it is. I forgot I had this in. Four metal cans, two specifically. One that's dull black, one that's shiny white, and they're full of water. And you put them next to a heater or in the sun, so that the only radiation they get is through only heat they get is through radiation. The black thermometer, the black can, heats up fastest, whereas the shiny white will also heat up, but slowest. All right? If you want to describe this experiment, it's simple. Get two, I don't need four, but get two metal cans, one's dull black, one's shiny white, put them equally spaced from a heater for fair comparison. The dull black will heat up faster than the white. They will both heat up, but the black heats up faster. What if you already have an object that's hot? It's not going to absorb heat, it's going to emit heat. So if you get a metal can, just one big metal can, and you have different colors of surfaces. So one side is dull black, one side is shiny black, the one side is shiny white and dull white. And then you pour hot water in. So it is hot. All of the surfaces emit heat. Every side will emit heat. But the dull black side will emit the most heat. The shiny black side will emit a little bit less. The dull white will emit a little bit less. The shiny white, barely any heat. Okay? So if you have two objects, one's shiny white and one's dull black, and they're both hot, the dull black cools down faster because it emits the heat faster. The shiny white cools down slower because it emits the radiation less or slower. Okay? I don't need the can, it was already drawn. Now, finally, just a few extra tidbits of info about heat transfer in general. First, if something is staying at a constant temperature, this means that it's absorbing and emitting radiation at the same rate. Because I just said everything emits radiation, but then that means I'm also getting a lot of radiation from the surroundings. So something like my phone is at a constant temperature. Why is it constant? Because it's gaining and losing heat at the same time. But if something is gaining more heat than it's losing, it heats up. And if something loses more heat than it's gaining, it cools down. So keep that in mind. Okay. Here are a couple of common examples where you have to describe multiple heat transferring processes. Here, for the frying pan, or you have a wok or something. Uncle Roger would be proud if I said wok. Huh. What methods of heat transfer are going on here? From the flame to the metal, that's conduction. To the pan, that's conduction. Through the metal, that's conduction. From the metal to the liquid, that's also conduction. But throughout the liquid itself, that's what? Convection. So you need to identify which process happens where specifically. Obviously, the handle is made of plastic. Why? Because we don't want it to conduct heat. I want to hold on to this wok as I make my fried rice or something. And I don't want it to get hot. But A more common example used in exams is this: the vacuum flask or the travel mug, or call it what you want to call it. Vacuum flasks, the one that you put like your coffee or hot chocolate in or tea in to keep it hot all day, is actually two containers in one, like a bottle and another bottle around it. And the space between the bottles is a vacuum. So what does a vacuum do? A vacuum completely stops conduction, convection, because they both need particles and there are no particles in a vacuum. So no conduction, no convection occurs through that vacuum. So less heat is lost through the sides. The only heat loss that can occur through the sides is by radiation. So step 2, we paint the surfaces silver, because silver is a bad emitter and absorber of radiation, which traps that heat inside. So even if the heat tries to leave by radiation, it traps most of it inside. So we reduce heat loss by radiation. So the silver reduces radiation. The vacuum stops conduction and convection from the sides. And finally, you need a lid, because without it, the liquid is going to evaporate and escape, so that's bad. And the air above the liquid is going to heat up and convect. That's also bad. You don't want it to lose heat. Okay? Good. Let's solve a few quick questions. Figure 5.2 shows a cross-section of a double-glazed window in the room. State the main methods of thermal energy transfer from the room to outside, which are reduced by this type of window. So what do we reduce when we have like double layers? Conduction and convection. Only radiation goes through. Conduction and convection. If you only write one of these, you lose the mark, because he said state the main methods, plural. So clearly there's more than one answer. Next. Here's a metal pan on a hot plate of a cooker. Copper is a metal. That's such a basic statement. Thermal energy is conducted through all solids by lattice vibrations. That's the same thing as saying, atom vibrations or atomic vibrations. Describe one other way in which thermal energy is conducted through copper. Through a copper. What do you explain now? The electrons. You explain what? The electrons. So free moving electrons in the metal absorb heat and transfer that heat to distant atoms or throughout the entire copper. Okay. By the way, electrons is probably worth a mark. Saying that they're free moving is probably worth the second mark. And transferring heat to distant atoms is worth the A third. Now, the outside surface of the cooking pan is kept clean by regular polishing. The moment you see the word polish or shiny or black, know that you're going to be talking about radiation now. Explain one other advantage of keeping the pan surface shiny. Wait a second. Shiny things are bad emitters of radiation. They're poor emitters of radiation. But how is that an advantage when we cook? Because when we heat, let's say the water, and it's getting hot, I don't want it to lose heat to the surroundings. It will regardless, but I want to reduce that. If the pan is shiny, it becomes a bad emitter of radiation. So less heat is lost from the pan when you're cooking. From the sides. Do you get the idea? Do you see why we want it shiny? Well, because the shiny surface is a poor emitter of radiation, which reduces the heat lost from the pan during cooking, from the pan surface during cooking. Oh. The thermal energy passes into the water and through the base of the pan. So that's done. It's gone through. Identify the main method by which thermal energy is transferred throughout the water. So not through the metal now, through the water. So that's a convection. So through the water is convection. Very nice. Now, before I move on to the last question here. How does this reduce convection? Here's the thing. Will the hot air in my room ever be able to escape the room? Because you're asking, how does this gap prevent convection? When I mean convection, I mean it reduces the heat loss by convection from my own air. Like my own air doesn't escape, gets trapped. So does my hot air escape if I'm heating the room? No, it doesn't. Sure, the surface gets hot by conduction, but then this is not a very good conductor. And even if it starts to convect, this air is trapped as well, so it can't escape either. So there is no air being lost out by convection. Do you get the idea? Very good. Good. Final question. I like this one because it's a mix of convection and everything else, and radiation as well. Figure 6.1 shows a road next to the sea. On a sunny day, the sun warms the road. On a sunny day, the sun warms the road. Describe how the energy from the sun reaches the earth and warms the road. Ooh. Wait, how does energy from the sun reach the road? What's the method called? You're gonna say, oh yeah, it's radiation. That's easy. Fantastic. It's good that it's easy. But here's the thing. Why is it worth 3 marks? Why is it worth 3 marks? What do you think? Because you don't just say, oh yeah, the heat from the sun reaches the earth by radiation. You have to describe the name. What's the name of it? Oh, infrared radiation from the sun is absorbed by, oh, hold on. Infrared radiation from the sun, right, is absorbed by the molecules of the road. You mentioning infrared radiation, right? You mentioning infrared radiation is very important. Okay? You mentioning infrared radiation is very important. Okay? Now, because that's a mark on its own. Sometimes even two. Like radiation is worth a mark, infrared is worth a mark, absorbed by the road is worth a mark. So, by the road. The temperature of the road is now greater than the temperature of the sea. The surface of the road is black. We're probably talking about radiation again, maybe. Suggest why the temperature of the road is greater than the sea. Well, because it's black, right? What's the feature of black? Is that black is a good absorber or a better absorber of infrared radiation. So that black color is a good what? Absorber of infrared radiation. Okay. The air above the road is heated by the warm road. Describe how this affects the molecules of the air. So the air over here is heated. So what do the molecules do? Like the air molecules here, what do they do? They move faster, because we're talking about the molecules now. They move faster and they also move farther apart. So they move faster and farther apart. If you want to say the speed increases and the spacing between the molecules increases, it's also fine. If you want to say they gain kinetic energy and they move farther apart, that's also fine. If you want to say they gain kinetic energy and they expand, that is not fine. Never say expand, you'll be arrested. No. Never say molecules expand. Keep that in mind. Finally, a cyclist is traveling along the road and notices that there is a cool breeze blowing in from the sea to the land. Explain how convection produces this breeze. You may include the diagram if it helps your answer. We don't really need the diagram, but I'm going to sketch what's going on up here. Let's say this is you, the cyclist, on your bike or scooter or something, like you're going to sit on this thing over here. And you're zooming through. But then you feel a nice, cool what? Breeze. So cold air is moving towards you. Well, think about convection for a second. If the ground is hot, then the hot air from the ground rises what? Up, because it's less dense. So what replaces it? What comes in to take its place? Cold air from the sea, because we just said that the sea is colder than the ground. If you want to draw the rest of the convection current, be my guest. Like the hot air goes up and the cold air goes like down, but this happens at a much larger scale than we think. So do I need to sketch? Not really, but sketching will help. Okay. So what? The air above the ground gets hot, becomes less dense, and rises. Becomes less dense and rises. And it is replaced by cool air from the sea. So cool air from the sea, from above the sea, comes in to replace it. You do not need to sketch. That's it. And that, ladies and gentlemen, is Unit 2.